would it be sufficient to see this little screen, or we need to project on a bigger one?
This looks good.
Anyone objects little and wants bigger one?
This slide is okay.
Okay, because if we are there, then we'll be able to.
We'll lose Levi.
Yeah.
And probably we can switch off lights so to see it better.
Levi, do you see shared content on your laptop? No? So you see it only on the screen?
Let's see or not watching.
So, thanks for coming. Today we have a regular group meeting with research update by London Johnson, and he will tell a story about charge transfer at the interface of nanostructures.
So, thanks for the introduction. I'm going to be talking about exactly that. So, the systems that I am looking at in particular, it's all perovskite and titanium dioxide. The differences between them are the linker groups on the titanium dioxide. So, there's hydroxyl linker groups, acetic acid linker groups, kind of a flipped acetic acid linker group where they're just kind of swung up, and then the same titanium dioxide but with a different perovskite structure. So I suppose I should mention, in particular, I'm just getting things going with these two at the moment. I'm getting coupling files going for all the other ones right now.
John, I'm trying to talk.
Everything else that I need to actually calculate the figures that you're going to be seeing later for these models.
So what is the logic to choose these configurations?
Which ones?
What is the logic? Why? What's the difference between them, and why they're selected this way? What are expectations? What are the goals?
So I guess the goals are to see ultimately which of these would be better or worse for photovoltaic devices. So I mean, that would involve looking at charge separation, relaxation times, things like that.
So I can hear it, but they cannot. Yeah, it's very usual.
You have many hydroxides, right?
Why did it switch? What happened?
Then why is they located kind of in one spot instead of being spread over the entire surface?
I've never been able to see time.
I am not.
Like,
Thank
it
you.
looks like they're clustering together, right?
Yeah.
Like this.
I guess I don't know exactly why they would be doing
I
that.
think they did it,
Happening with acetic acid, probably due to hydrogen.
which makes me kind of not want to even come here.
So this is after optimization, or?
Yes, this is after.
But you started
optimization.
like they're layered on the surface, and then they kind of came as a cluster, or you
They-
start already as a cluster.
They started more or less as a cluster already. I mean, they were.
But then what is the reason? I thought that you're supposed to have these ligands on the surface rather than just as a cluster. In other words, each of these molecules should be coordinated with your atoms on the surface of the perovskite, right? Either lead or iodine, I don't know what exactly the ligands it
was always
should
dark.
be interacting with.
Oh, you
Do
don't
you
want
have any image for initial geometry?
I do not. No.
But you're saying that it's not like you're really having each molecule sitting.
No,
on the surface.
no, it's not set up quite like that. I mean, to be honest, I guess I was just kind of handed these geometries, so I just started working with what I had.
So someone gave it to you, or
Yes.
you make it by yourself?
I did not make it by myself.
But what
Who
is
was-
your
who was making
what
it?
is your vision of?
Let's find the
what-
person who was making and
It's
ask
so,
him.
it's so hard to find this person. But what is your vision of logic behind this geometries?
You know what he's doing?
Like, what? Probably one
I
is
think he
looking
knows
for
what he's doing. I don't know
optimization
if
of
he knows
charge
why
transfer,
he's
but
doing what he's doing.
which of them are
that
expected
make
to be
sense?
better, which
He
of them
wants
are
to do clusters,
expected
but
to
he
be
doesn't know how to
worse?
explain why he wants to do
Why why the ligands
No.
are on titanium
He,
and not on the perovskite?
he is doing what was given to him. He
Well,
does not know why they are.
I guess I already know from a little bit of experience that the hydroxyl model
Well-
will be a bit better than the acetic acid.
But they are on the titanium or the. So actually,
I don't
it's hard
understand.
to say from these images. So these ligands passivate in titanium dioxide quantum dot, right? So the reason for these
That's-
ligands to be on a quantum dot rather than on a perovskite
Yeah, I'm
surface,
on Slack now.
Yeah, I saw that.
I could
or
make
they,
a
or you
guess.
start with
Yeah, I
perovskite
don't
and
know,
they move
maybe
to
I sent it to
titanium
him.
dioxide.
I don't remember.
They did not start
You know
on
how
the
Brandon
perovskite. I
has
don't
random gifts
So
with
you already start
PhD?
them being passivating the
On
surface of
Facebook?
the quantum
No,
dot.
on Slack.
I would imagine that would be
No, I
easier
just
in
need to
terms of
find out
application.
because
I don't know how well that would work if you were to try to, I guess, I don't know if passivate is the right word in the context of the perovskite, but if you were to try to attach them to the perovskite, that might
But
not.
then they're different in a way that you have kind of a layer of your ligands in between the perovskite and the quantum dot. In your case of hydroxyls, right? The very right one, the very left one. Same for the acetic acid. And when you call flip, it might be again just a view because it's really hard to say what exactly is there. But then here you kind of don't have ligands, you have really quantum dot, perovskite. They interact like you have really titanium dioxide interacting with the perovskite. Am I right? Or the set one?
You still have some acetic acid groups on there. The difference is that instead of having one that's like pointed straight down at the perovskite, they're all kind of spread out to the side. I guess it's not really all that easy to see. You can see one on the right end over there that's kind of sticking out. But it's
But again, you probably need the distances. And you can really check whether you really having some kind of distance between titanium or oxygen and again iodine or lead or whatever your perovskite. Are they coming on a proximity, on the length of the bond? Or they're really far away and it's not really, and it's just really phase absorption? Or you're creating some kind of coordination between this ligand and lead and so on from perovskite, right? So I think you probably need to think about really initial geometry and your final geometries in a sense that what is interacting with what, right?
yeah.
Is it phase absorption of your quantum dot to the surface or chem absorption?
I would
the
say
bond?
it's phase absorption. If
Neither
I,
of these systems creating a bond with the surface.
I don't believe so. I haven't actually looked at the distances of these models, but these ones I want to say are on the order of like 4 to 6 angstroms, somewhere in there. So like a little bit farther than a usual bond would be.
Okay, but again, you probably can. It's a very easy analysis, so just kind of a first step to understand how they different, how they interact, and yeah, what is we still kind of why these ligands were chosen or why this type of molecules were chosen. Do you know?
I don't know the actual reason though.
What is your thought? If you're thinking like a chemist.
I would assume one
The chemist.
wants to bind.
You know how chemists usually think.
No, just chemists think. Next question.
So, and you can ask people in the audience, like, or try yourself, what is the role of ligands? For example, Daniel and Aaron were
Dangling bonds to not
presentations
have in the
on
band gap on you.
perovskite with ligands. And probably in their presentations there were some rational
to facilitate
for putting ligands on
the
perovskite? Do you do?
moving of the states
So
inward.
what was the
Yeah, I know it wasn't that logical,
rational
but you
for
know,
putting ligands and which you
who is
maybe do
that
not need?
on this shirt?
So the ligands are mostly there to
It looks like
lower
Dr.
the
Who. There you go.
what would the actual word be? I guess like
But
the
he's
potential
not-
barrier
he's
in a
not-
sense to make the charge transfer easier.
But he's not in so
Read the quote.
made it.
But at the same time, you need to balance that with
I don't know what that
not
means.
allowing your charges to flow back across as they relax and then recombine, which would kill your efficiency in a solar cell.
The hat. The pad is called the fez.
Very general.
Yeah.
Which applications are pursued specifically by Aaron if you were attending his presentations?
Something with photo. Right?
Ask him directly if you don't remember.
I guess I'm probably thinking about this too generally.
It's maybe
What's-
emission, right? Mainly
We're
this
talking
is.
about the quantum dot or
Yeah.
thin film?
Quantum.
And what about the quantum dot?
I guess what's the application? Well, because those are the ones that you're doing with hobby, right?
Yeah.
So that would
Experimentally, yeah.
yeah. So you're
So you
doing
passive
emission
agents
with
so that-
those, right?
They become good emitters.
Yeah.
So emitters. Do you need emitters for photovoltaics?
I do not know.
So
You
do
what? You do not?
No.
I
Just-
need absorbers.
You don't know or you don't
I
need?
no, I do not need
Okay.
emission.
So Aaron is and Daniel are looking onto ligands on perovskites to make them good light emitters.
Mhm.
Do you need light emitters?
No.
So therefore you probably are not caring much about ligands on perovskites.
Oh yeah. Okay, that makes
Okay.
sense. Yeah.
But do they naturally there, just from the air, from a solvent? Probably you expect, like, if you want to have a realistic structure, the ligands will be there anyway.
So what was your once in your history you were synthesizing solar cells of perovskites?
Mhm.
So what were the conditions?
So I guess when I was actually making these, what I would do was anneal the perovskite onto a glass slide. Oh, sorry, actually, first I did the titanium dioxide, and after that settled, then I annealed the perovskite onto there. So I didn't. The method that I was using wouldn't be easy to actually attach any ligands onto the perovskite itself. It would be. I guess I don't know if it. Yeah, it would probably be easier to get it onto the titanium dioxide if you were to try to actually passivate things with ligands.
Okay.
Yeah.
So actually, maybe you already described that I missed somehow. So in your system, you have a perovskite, titanium dioxide, and ligand, right?
Yes.
Which one is the ligand, which one is perovskite, and which one is titanium dioxide?
Perovskite, titanium dioxide, and then ligand.
Oh, okay. So this is actually Levi's question. Is there have any vacuum in the top of this one?
What's that?
Vacuum? How big is your cell and how big is it?
These two have somewhere between
30 by 20 by 20. Approximately.
How long? What is the vacuum in the top of the in Z direction? Yeah.
I want to say this is about 15. No, it's probably longer than 15 angstroms. It's probably more like 20 angstroms tall.
So there are 10 angstrom, 5 angstrom vacuum in each side.
I guess I don't know if it's on each side or just all on one side, but yeah, the gap between adjacent molecules would be about 10 angstroms, maybe
Yeah,
a little bit
what
shy.
is the vacuum on the top of the cell, top of the unit cell?
I'm not
This
sure off
question
the
is-
top of my
Why
head.
would it matter if it was 5 or 10? Because when it's repeated, it's going to be 10 anyway.
Yeah,
No, it's because there are calculation in the box. Because if they have a very small vacuum, it could feel the interaction with the next cell. That's why maybe he's asking that.
yeah. The gap between like the bottom of this perovskite and say the next titanium dioxide below it would be about 10. I couldn't tell you exactly if it's 10 directly above this in the cell or if it's 5 here and 5 here,
Okay.
but it's about 10.
Okay. And other questions about, I'm just wondering about the ligand you said. Is it because of in your initial geometry, maybe distance is too high, you didn't feel the interaction with the titanium dioxide is rather, that's why it's go to the, what is it called, perovskite cell. Is maybe because of your initial geometry?
You're wondering why these are being pulled toward the perovskite?
Yeah, initial question is why is pull all ligands towards the perovskite only?
Toward the perovskite only?
Isn't it the initial discussion was why the ligand is not on the top, on the surface of the titanium dioxide?
Mm-hmm.
So is it because of maybe initial geometry? Initially you put the ligand is very close to the perovskite rather than the surface, and then after optimizations is pulled by the perovskite only.
These would have started more on they would have been on the perovskite side, I guess, because the ligands wouldn't really do you any good being anywhere else. They wouldn't really have any.
Yeah, I'm just wondering, I mean, maybe it could be.
Well, any other questions, I guess?
I didn't get any questions so far.
All right. So I guess for the rest of this, I'm going to be talking about these two models because these are the ones that I'm just recently getting data on about the electron dynamics. So these are just the actual numbers from some runs that I was just doing. So these are the bands that I started the hole in and the bands that I started the electrons in. The HOMO in the hydroxyl case is 453, and then likewise down here it's 480. And this is the oscillator strength of the transition that would get the system to this state. And then these are the relaxation constants, I guess when you actually let it relax starting from this state. It's organized a little bit weird, but that was just easier for data entry because I was in a hurry.
This table misses gaps for each of excitation. What's excitation energy? Does it go into increase of the what is the principle to arrange this table?
Oh, I just went by the oscillator strength because I was just working my way down the list from there, so that was kind of the natural way to organize it, I guess, to try to hurry up and collect some data quick.
Okay, what about transition energy? Does it increase, decrease, or it is completely random?
There's not really a very solid trend in the hydroxyl case. I guess the relaxation rate of the holes in the acetic acid case decreases as the excitation increases. These last two down here are a stronger excitation than all of these. These are all more or less the same gap between the states. But the electron relaxation constant actually increases quite a bit as you increase this excitation. But yeah, these ones more or less hang around the same values. They don't really seem to change very much.
So, what is your ideas how one could represent this table graphically? If you see any trends, like you show 5 columns, maybe you can add the 6th one with transition energy.
Yeah, that would be really easy to do.
Would you expect to see any linear correlation between any of these columns, and how would you represent it graphically?
I guess are you trying to get me to see if I could plot the energy gap law? Or
Yes.
Okay.
Yes.
So.
And you can enlighten us what it is.
Well, I'm actually not. Okay, so I'm not 100% sure what exactly the energy gap law would state. I mean, is it more so the gap of the individual excitation, or is it the band gap between HOMO and LUMO that's more important for the energy gap law? Because everything that I've been seeing has been pretty vague, so I'm not really totally sure. I would think that it's the individual excitation, but I mean, this certainly doesn't support that, so I don't know.
But you can try to identify it. But
yeah.
What would be your x and y if it is two-dimensional plot?
The x-axis would be the excitation, or the energy difference between these two states, and then the y-axis would be the relaxation constant.
And eventually you may expect to see linear trend.
Yeah.
Okay.
But again, why is it like each of these energies going? So you excite a different energy. So what exactly your columns show? I don't understand. Your H initial and E initial, these columns. This is during the time scale when it's really do dynamics going from first 450 to the wherever your HOMA, or this is different types of excitations, and then you look how quickly they go to HOMA. Like I don't understand what exactly means when you say H initial, E initial.
So okay, so essentially.
And why you have different numbers here.
Yeah. So if you were to imagine the system with all the electrons in the valence band and all the holes in the conduction band, then the oscillator strength that I'm listing here would be the oscillator strength to kick an electron up to this orbital and the hole down to this one. So to jump an electron from that orbital to that orbital.
But are you choosing, again, because we don't know the energy of these transitions, so each of these transitions having similar energy to each other, or they're very different in energy?
They're pretty similar. They're all within 1 eV of each other. These ones might get more towards like 2 eV between here and here. But they're.
But you were picking the most bright transitions. Like
yes.
What was your kind of criteria to show these transitions?
So I looked at the OS strength file, and this is the first row, basically the second row, the third row, the fourth row. So I just worked my way down the OS strength list, is what I did here. That's why it's organized.
This is the strongest oscillator strengths among all transitions, or they are among this energy range. Like you're choosing transitions with, let's say, 2 electron volt or whatever, 1 electron volt excitation energy, which are the most brightest one. Or you just like the energy might be very different. You just really kind of order them in the range of oscillator strengths.
I ordered them by oscillator strength. So these are the top 6 of
443 to 475
likewise.
might have very different energy comparing to 450, 467 transition.
Right. Yeah, that is definitely possible in here. Yeah, if I remember correctly, though, the energy differences were not very high. Certainly no more than 2 eV, I can tell you that much for sure. Yeah.
Okay, I don't really understand the whole KE and the KH. What does that mean?
That is a constant that gets used in the calculation of the actual relaxation rate. So the rate.
How fast it relaxes, or how fast it goes?
Yes. Yeah, so you excite the electron up to some higher state, and then it'll work its way back down.
Or vice versa.
Yeah. Or the hole kind of working its way back up. Okay. So the relaxation rate will tell you how quickly that will happen. And to figure that out, you take E to this times some other, times the time, I guess. Okay. No, not to get the relaxation rate. That wouldn't make sense. I guess I can't remember exactly what the other factor is.
I understand what you're saying. So why don't you have one for that one?
Oh, this one started in the HOMO, so it didn't go anywhere. So this would be infinite.
Oh, got it. Understood.
So it is how quick it cools. The charge carrier cools from excited orbital to either HOMO or LUMO.
Yes.
Okay. Then.
So I guess for your system, do we want high relaxation rates or low relaxation rates? And I guess in that sense also too, are we looking for high oscillator strengths or lowers?
So the highest oscillator strengths are the excitations that would be most likely to occur if you just shine incoherent light on it. And so that's, I guess, why I kind of looked at just the highest oscillator strengths just as a quick baseline thing, just to get some data down and see what's going on with these. So you would want a slower relaxation rate to prevent recombination, because if they basically converge back towards each other extremely quickly, then you've got a lot higher probability of them just recombining, and then you've lost your excitons, so you don't get any current out of it.
Wait, so is a high K or a low K good? Like
lower K would be
so
better.
So like 0.8 is better than 1?
Yes, but there is a problem with this configuration, which actually I think is on the next slide. So, okay, so in the hydroxyl case, you have.
Jabit.
Oh, yeah.
In the previous slide. So if I'm not wrong, I mean K, E, and K is actually Braden and Levi's question too. These are rates for relaxation to the initial stage to the frontier orbital, right?
Yes.
Okay.
What's the rate for recombination? How can you find it from your data?
I mean, you use the K, I guess, but.
Well, you just need to run it for your HOMA and VUMA between HOMA and VUMA.
Or even simpler. If it is only a two-level system, HOMA and VUMA,
Yeah.
and there are no factors other than non-radiative proteus, you just take specific matrix element of RRR matrix.
Oh,
You
yeah.
just need to find the right one.
Yeah.
That corresponds to pair of HOMA and VUMA.
Okay, yeah.
So next question is, I'm just wondering why you plot the OS strength only here. I mean,
That's opposed to, like, what is it that I'm missing, I guess?
what is the significance of this column? Why you plotted only this column, not the transition energy?
Because I was in a hurry and I wasn't thinking about it very much. I made this maybe an hour ago.
No,
I had literally just got things to start working, like, today.
okay, so because you already plotted, I mean, listed as a ascending order, so descending order. So and you also said that the bright transition only depends on oscillator strength.
You're asking me
Yeah, I mean,
if the brightest
yeah,
transition?
is the brightest is the only higher OS strength, or it depends on something else too?
Aren't you not looking at brightness?
Yeah, no, this wouldn't tell you the brightness of it. This would tell you the likelihood of your system being excited into this initial configuration.
Because he's not looking at
Okay.
light.
But wouldn't it correspond to the absorption cross section, which you can measure from experiments? At
I'm
this
not
energy?
familiar with the term.
Well,
absorption
wherever
cross-section.
you measure in experiments from spectroscopy, right? From
Yeah.
these absorption spectra.
Okay, so the absorption spectra those would be related to the transition energy, not the oscillator strength. So I should have the transition energy.
Your
here.
spectra having two axes, right? One is energy and another is intensity, or also it calls energy density. How we call it for the black body radiation? Energy density.
Spectral density.
Spectral density. Yeah. Spectral density, is it more familiar term?
Yeah.
Okay. So which actually telling you how intensive is the transition at this specific energy, right? And this is why you have, in some cases, peaks. In some cases, you have kind of gaps or no
Right.
response at all, right?
Yeah.
So your oscillator strength is directly related to the intensity of these transitions. And technically, you can just kind of check the units and recalculate it in a units, so it would be directly comparable to the spectral density or absorption cross-section, wherever they measure really in experiments.
Mm-hmm. Yeah, this would just tell you basically how high your plot would be at any
Yeah.
given
So in
energy.
other words, this is your brightness of the transition, right?
Oh, that's what that
Well,
means?
again, if you say brightness, thinking that this is emission.
I was thinking brightness. Oh yeah, actually, yeah.
Yeah, I mean, if
Got
you're
that
thinking
wrong.
about emission, the brighter it's more emitting,
Yeah.
right? Then it's probably not directly connected to this one, because actually, again, because you need to relax your system and let to really get your emission at the lowest excited, at the minimum of the excited state. But you can use the jargon bright or dark state, right? If oscillator
Yeah.
strength is 0 or close to 0, it's a dark state. Means you cannot absorb at this energy, or you cannot emit at that energy. And if it's the larger this number for oscillator strength, the brighter the transition is,
Yeah.
right? So it means the more intensive
Yeah,
the
I was
spectral
thinking,
density
like,
is higher, right?
color palette, not
Right.
brightness. I don't know.
So you cannot directly use these values to compare with experimental measurements, what they really like with experimental spectra. But you can scale it based on the units, right?
Mhm.
And then you will get something what really can be measured in spectroscopy.
Yeah.
So Braden's wants to know that what is the physical interpretation of different or importance of the different relaxation rate in the both system.
That would essentially tell you how quickly your electrons and holes will basically converge back toward each other. So if this is
Not
higher,
converge back to each other.
well, towards the hole,
Hole to HOMO and LUMO.
yeah,
For a combination, it will be fixed number for a given system. It will not change depending on excitation. Upon it gets to HOMO and LUMO, it will be the same rate for a
How
combination.
quickly you reach in the lowest possible transition, right? Or the optical band gap, in other words.
yeah, yeah.
Right? So you start wherever your energy is, probably far away from the band gap,
Mhm.
but you end up close to the band gap.
Yeah, his question is why is different in the two different systems in presence of acetic acid and hydroxide link.
This is clear because the difference in this passivated molecules really play a role somehow, right?
Yeah,
Yeah,
you
what-
have different pathways for the electrons and the holes to follow, essentially. So it's, I mean, these aren't going to be the same because it's a physically different
One
route.
can
I guess, that they're
analyze deeper and see if there are different styles of hybridization between this donor and acceptor, and it will affect for sure.
But you probably will talk about it later.
Yeah, this is
Last
all
slide yet.
very
And
preliminary.
it is not his last talk.
But I think again, so when you're presenting, right, it would be because think about your audience first, right? For us, these numbers mean nothing. You really need to clearly present the physical meaning of each of your columns, right?
Mhm.
And then kind of gives that, not like line by line, but probably the overall kind of message that looks like, yeah, acetic acid, right, a linking group, it definitely provides for electrons, it's slow comparing to the hydroxyl linking group, right? Not very much slow, but a little bit slow. And I think for the holes, it's a backward behavior. You have around 2 or 3, and this is around 1. So you have quicker hole in one case of linker, and quicker electrons in the other one, right? And this is your main message from this table. We don't need to really go to line by line. And of course, it also would be interesting, another message number 1, I think probably each of us can get it if we look and compare these numbers, but you can help us, right? We don't need to spend our time, you just tell us. The second message you can say, like, you comparing, at each of these systems, you're comparing different excitations. But then the question is, again, showing the number of levels for us tells nothing, even if you say, oh, HOMO is 453, so what we should take, okay, 450 is our HOMO minus 3.
Well, again, this was just
so you
that I could
probably, I understand
hammer
we're in
it
a
out
rush,
in
but
like 5
again,
minutes,
you
know.
can briefly look at least on your energy range, like even saying like around 1 electron volts, but how far you really excite from your gap. Like 1 electron, I don't know what is your gap. If your gap is very small, then 1 electron volt can be still very far away from the gap, like twice the gap or maybe 3 times the gap, right?
Yeah.
So probably then some message should go with how this, let's say, the brightest 450, 467 having kind of the probably one of the largest rates, right? The quickest. Your case,
Oh, the top one,
128.
okay.
Yeah, looks like it's the largest one. If I'm not, quickly, kind of. The other ones not very different, but again, you have some smallest ones. So probably it also depends on the energetic of your excitation, and this again probably depends on a band character, orbitals character, where you excite. Let's say if you excite 450, 481 with the smallest rate for the electrons, you probably excite, I don't know actually which system you excite. You excite the perovskite? This is analysis where
Just
where
the question
initially
that
you
I
excite
wanted
the
to ask.
system. I excite in perovskite, I excite in the titanium dioxide quantum dot, probably not because your quantum dot should have very large band gap, right? You should not expect that there would be some excitation on the quantum dot. Or maybe, yeah, if your levels are very hybridized, if your orbitals are very hybridized, so then you excite some kind of charge transfer, which is not really charge transfer because of the very strong hybridization.
So this table needs to have one more column. So we discussed that it needs
The
to have
type of excitation.
number 6 for energy and column number 7 for type of excitation, because you have two entities,
Right.
perovskite, and your pair of initially activated orbitals, they may both reside on perovskite, will be neutral excitation. They may both reside on titanium dioxide, another neutral.
Which is
They-
probably not the case because you're not expecting that you have excitation at
But
around
it's
1
better-
electron
it's
volt on
better
a
to check.
titanium dioxide quantum dot, right? But yeah, you can check it for sure.
It's better to check. And there are two other opportunities when the electron is on perovskite, hole is on titanium dioxide, and opposite. Hole is on perovskite and electron on titanium dioxide. And this question is a little provocative as a setup because your next slide partially addresses this question, but only for two excitations. The thing as you present on next slide has to be done for each of the excitations that you show, and
Right.
in the column you may mention whether it is neutral or charge transfer excitation.
Yeah.
But right now, again, looking on these numbers, and again, I'm mainly looking on the electrons because it's too much for me to look on the holes at the same time. But for electrons, the difference between the rates is minor, difference with respect to the where you excite, wherever your character of these orbitals, is a minor. It's maybe the reason because your energy is close. I mean, all these excitations are close in their energy, and they all have the same character. Or maybe they have different character, but then maybe it's not very much really affecting the rates, right? But the difference between linking groups or between these passivating groups, right, is definitely having much stronger effect comparing to the where you excite. But again, where you excite, until you really make this analysis,
Well, right.
it's
Yeah.
really probably too strong right now to say, because it might be really very close in the excitations and we're just looking pretty much on the same band, right? But this is probably very interesting to check.
Yeah. Oh, yeah. That's kind of the next step. Is after now that I can actually do these with these systems, I'm going to do it with the other ones as well, and then I'm actually going to look at where the orbitals are lying, and
now,
actually seeing which
I think
ones
we're
would
all
be
intrigued
applicable.
because Dmitry already put this intrigue, so partially you might address this question in your next slide.
And Javid has another question.
It's not mine actually.
But maybe we
coming
move on
from
to
this
the next.
side.
No, but maybe we move on to the next
Yeah,
slide,
it's
and then
kind of
maybe
similar questions,
maybe
yeah.
maybe it helps to answer these questions.
So those kind of things, they are asking that do you have a PDOS and why you thinking that is ligand effect of this relaxation rate, because the ligand is not perfectly passivated with the quantum dots or something like that.
I have not
And you need
analyzed
to
this
take
yet.
that.
But I think we need to move on. We don't
Yeah.
know what's going on next. I didn't really look on this.
And
page.
45 minutes is enough for two slides.
Wow. Okay. Good. At least
So-
we have something.
Yeah.
to
Right,
discuss.
yeah. So just to kind of give everybody an idea of like what the HOMO and the LUMO actually look like, this is what they are, I guess. So the blue clouds, I guess, are the HOMO, and the red clouds are the LUMO. So in the hydroxyl case, they're actually distinct. In the acetic acid case, they're both localized on the titanium dioxide. So this is not exactly ideal for a solar cell. Because as things relax, you're just gonna end up with your charge back on here.
So style of ligand affects offset of frontier orbitals of mutual arrangements of HOMOs and LUMOs of this donor acceptor.
But my understanding is, again, you expect that you want to have your whole electron or whole transfer, your charge transfer, should happen quick, right? And you probably expect that it should happen much quicker comparing to these relaxation rates or relaxation times when it's going from where you excite to these HOMO-LUMO levels.
You're saying that the excitation would be quicker than the
Not
relaxation?
excitation, the charge transfer.
Or the- yeah,
First
sorry,
you
sorry.
excite, right?
Yeah.
And then you probably expect that you expect that efficiency would be higher if it immediately, very quickly moves either electron or hole. Some of these charges will move to your interface, right? Then you actually don't need to worry about what is your HOMO and LUMO. It's really more like how quick, like what exactly the character of your initially excited state, and whether they really kind of create this charge transfer character at faster rates than reaching your homoluma. Right?
Actually, yeah, that's
The quicker you get in your charge transfer
what
state,
you're
right?
looking for.
Yeah.
The more efficient it would be.
Right. I mean, in this case, though, you would have the problem of
Based on
the possibility, I guess, of going directly back down from the Lumo to the Homo. Because of the...
Because again, you expect that you excite not this type of charge transfer states,
Because
because
the
usually,
provides
and again, this
you
is
the-
related to the character of your transitions which you're choosing, right? So those transitions which you choose, the bright ones, neither of them probably really having this charge transfer character type, because usually these transitions should be optically inactive.
Right, yeah, no, the...
So you probably
yeah, the ones with
excite,
high
you probably
oscillating strength
excite,
will be kind
like
of on
mainly
hold.
you probably excite the perovskite. So initially your
Yeah.
excitation is on perovskite, right?
Mhm.
And then when it's kind of relaxing, some of the states, maybe electron, maybe hole, might kind of jump to the state belonging to the to your dye, and this would be what you call charge transfer state. And this charge transfer state might be appearing not as the very last stage after final relaxation, but somewhere in between, right?
Let me add a comment. So it is not from me, it is from London. I don't know if he remembers it himself, but I will just verbalize what he has written in his in-class project 2 months ago as a conclusions. So his conclusions were that depending on the linker group, one observes two effects. First, mutual offset of the conduction band minimum for titanium and perovskite, and second, height of a barrier on this pathway of electron transfer. So the offset determines whether this configuration will ever be able to participate in charge transfer, because the rightmost acetic acid doesn't show charge transfer at all at the lowest state. And second, the height of a barrier, or just the rate of the photoinduced charge transfer, is how ligands, or the distance amount of vacuum between donor and acceptor, affects whether the charge transfer will be quick enough. And addressing both questions simultaneously is what London was posing 2 months ago. I don't know if your goal is the same today or you have different vision.
More or less the same, just a little more sophisticated these days. Alright, so so just today I'm now at the point where I can start getting these plots. So this one on the left shows the height of this is the, let's see, that would be the hole occupation. And so this axis would represent your orbital, where 0 would be your HOMO, and then you kind of work your way down. And this axis represents time. So essentially what this is saying is that right away your hole is starting in, what would that be, the HOMO -3. And it kind of decays, jumps into these two states, and eventually is completely localized within the HOMO. This is essentially the same thing except with electrons, so this is the LUMO, and these are, LUMO plus whatever. This plot is showing
The same, but it's kind of a snapshot, right?
Yeah. But yeah, this axis is the energy instead of position or orbitals or anything like that, and then this is essentially the same plot as this.
And actually,
except
look on this plot. It's already answering the question where you excite. Question was initially for your initial excitation. One of these, I guess, you're showing one of these excitations from this table, right?
Yeah. This is just the top one
So,
from the hydroxyl.
and can you now analyze it and say, so where exactly you excite in this case? Is it the titanium dioxide quantum dot, the perovskite, or the hybrid state?
This one starts out pretty much entirely localized on the perovskite. There's like a little bit of electron kind of smeared out all through here, but then
And this is
slowly
exactly
works its way up
what
here,
I'm saying,
and then-
right? So actually, before even reaching to your low state, and before really go into the full time of your relaxation, right? So you're already creating this charge transfer state.
Yeah, yeah.
Which is probably really a good feature anyway. The earlier
Right.
you get it, the better it
Yeah,
is.
more likely
right?
it is.
So based on your figure, on this bluish figure,
The bottom one here?
yes,
Okay.
yes. How quick charge transfer happens?
Oh, it's in the logs, yeah.
Yeah.
You can just finger it on the bigger screen, approximately.
Scan because
Just
Wait, what?
just approach the screen and show it by finger.
It's
Where
a
charge-
crossing, just
Oh,
number.
like where the
just
charge
unload the
transfer actually
number
happens?
from your graph,
So it'd be somewhere in here.
which is what's the number? It's 100. We
yeah,
can't
so
really
that's-
see the number.
About halfway between 1
it's
and
not a halfway,
110.
it's log
So,
scale.
So 10 to the minus 1 picoseconds will be
0.1.
100 femtoseconds.
yes.
And 10 to the 0 will be 1 picosecond. So
Yeah.
sometimes between 100 femtoseconds and 1 picosecond.
Right.
But technically, you're reaching your charge transfer in 100 femtosecond, sub-picosecond range.
Right, yeah.
It's extremely quick.
Mhm.
So you
Is it good or bad?
That's good.
expect it to be really very beneficial.
So I guess I plotted this thing right next to it just to kind of have something to compare it to. This is more or less the positions represented on here.
So is it saying that it's going from the perovskite to the bulletins, or I don't really know how to read this.
Yeah. So okay, so I included these here because I had no idea how to read these right away either. So basically, like the more yellow color would mean that there's an electron there.
Okay.
The darker, like purple, would mean that there's a hole there or a lack of an electron. So right away, it's all just kind of like the neutral blue where there's not really any charge going on there. You've got like some bright spots in here, you know, down here.
Is that because of the different charges of each of the atoms or each layer, or like why is it look different?
So
Like your density probably is really kind of spread because it's a
Mhm.
bulk semiconductor,
Okay.
right? So you expect that your density has to be pretty much delocalized if
Yeah.
there's no trap state. It's
So-
not really defect or anything. So that's why it's kind of going layer by layer with respect to
yeah.
that.
So I guess I could actually. Oh wait, no, there's a thing right here actually. So this would basically mean that you've got electrons kind of somewhere in here, kind of down here, and kind of down here,
But
like
the
sort of
blue
on the
is,
top
like,
and the
in
bottom of
bet-
the atoms.
The dark blue is in between the layers then?
The dark blue would mean that there's a hole in that.
Yeah, so that's like right in between the layers?
on the surface of the layer.
Yes.
Can you explain the composition of atomic model? Probably if you approach the screen and
Yeah, what is
feel
your red,
free to-
blue?
what is the
type of
top layer of
atoms?
perovskite? Which
Wow.
types of atoms are there?
Compare the Z with the image.
These
Well, yeah,
are.
I know. But
The red
since,
one-
Like,
These are
isn't
bromide.
So he's-
Oh, you have bromide, not iodine,
Or
okay.
wait. Yeah. No,
Brom-
those ones are the bromide. The bromides are kind of red. These ones are leads, and these are cesiums.
Which one?
Uh,
The yellowish kind of? This is-
I might have those backwards actually. Memory is not my strong suit. I want to say that these are leads and these are cesiums.
Yes,
Okay.
So on the top you have leads, mainly.
leads and bromines. And as a reminder to yourself, you can just write it on the slides.
Yeah.
So the top layer consists of both leads and bromines,
Mhm.
and the left bottom figure, where you ask why it has both bright and dark spots in one layer.
Because both electron and
Because-
hole are on a
Electrons are
Perfect.
likely on a lead in this excitation, and holes are likely on a bromine. And they have different shapes, like maybe it is S on lead and P on bromine, and they coexist in approximately the same space area, and therefore it is little fringes, oscillations. Make sense? Okay.
But again, you probably would be very helpful in addition to show not only homoluma, as I said, right? But
Right,
your
yeah, but the
initial
actual states
excitation,
that
right?
start
Because
here,
you know
yeah.
your orbitals, you can really just show the densities of your initial excitation, intermediate state, right? After whatever 100 femtosecond, and then yeah, homoluma as you already showed.
Right. Yeah. But yeah, these are kind of nifty because this would actually allow you to sort of plot out the trajectory that the electrons and the holes take. Um, so yeah, I guess I have like another one of these of just the
So
second.
this is another passivation of what is it?
Yeah, this is
Or it is just the same passivation and different initial conditions.
different initial conditions.
Ah.
So
Okay.
so what I did is I just took, this is the first page, this is that second slide, and then the one after that will be this one.
Okay.
So, I mean, it's
And
the same.
how is
business,
it
I guess.
different from previous one? Can you kind of go through it?
This one isn't as localized on the perovskite. I guess you've got a little bit of your electron density on the titanium dioxide to begin with here. So it's not really a complete charge
So
transfer,
it's
I
having
guess
a little bit hybridization with
Yeah.
your molecule.
Yeah.
I mean, with your quantum dot or whatever it is.
Um,
And it looks like you get into this really more charge separated state, charge transfer, charge separated state earlier than
Yeah.
previous case.
yeah, because this one hits that by, I guess, yeah, the 100 femtosecond mark.
How many layers do you have in the perovskite layer? Because it seems like your hole is like layer. There a whole layer and then electron layer and the whole layer. It's kind of more symmetry.
So there are 18 leads, 18 cesiums.
Means layer, how many layers?
Oh, in a layer?
4 probably, right? Like if you take out the 3D effect on your
Or where?
image, probably would be a good idea here
Yeah.
to take out the 3D effect and have just a projection.
Right.
Then
Yeah.
it would be more layered because right now they
Yeah.
have this how it calls the
I had
perspective.
these pictures handy, so.
That's why it's
I
hard to
just
say.
threw
But I
them
think
real
I
quick.
think it's like 1, 2, 3, 4 or 5, right? Layers kind of.
But number of unit cells is likely 2 because there are 2 layers of cesium, and each layer should have cesium.
No, you have one layer with cesium and one layer without cesium, right?
Yeah, so I guess are you talking about like this is like a layer and then this is another layer and that is a layer?
Based
These
on
are
your
like
crystal
alternating
lattice.
between bromine and cesium.
Electron hole density also seems like layer wise. That's I'm just wondering.
Oh, you're saying in here?
Yeah.
Yeah.
It's kind of.
But then again, it's maybe because of the different shape. Don't forget, S electrons are more localized around the atoms, so they will be taken just like that's why the kind of blue is
Yeah.
more kind of aligned with the layer. And this light blue or kind of yellowish colors, they probably p orbitals, which are more spread over the space. So that's why the density will be kind of far away from atoms, more far away. And that's why it's
Yeah.
not really sitting on a layer. It's kind of the same question which Alisa asked before too, and Dmitry was addressing, right? So it's probably like your lighter layer and your bluish layer, they're kind of coming from the same atomic layer. But because of the difference in the S and P character of these orbitals, that's why your blue is more like really on a layer, and these yellowish colors are more like a little bit outside.
Okay.
But they probably coming from the same atomic layer. But again, if you just make your orbitals along these several steps, right?
Right. Yeah.
this would be clear how it's spread.
Yeah, that's definitely on my to-do list. And then with the acetic acid model, I'm not quite as far as I was in this one. I don't have the band out files that I need yet for these plots, but I can still get these ones at least. So this is I guess, the highest oscillator strength transition for the acetic acid. Yeah.
Or is the conclusion slide?
I don't have.
Or maybe you can.
The work is in progress.
Maybe
Yeah.
you have verbal conclusions.
I still have a lot of work to do.
No. Conclusions on the things which we know for sure now based on your data.
Not as your conclusions, not as
Not future perspectives.
workforce machine. Conclusions as a strategic thinker about the overall area. Like, what is the impact of your findings to the community?
And actually, I was kind of telling you these conclusions in a second slide where you had this table, right? I told
Oh,
you 2 things which you have to think about.
yeah. So basically, you get, I guess, a more dramatic increase in your relaxation rates as the energy goes up with this one. You seem to have just a generally higher electron relaxation rate in this model, though, I guess.
Maybe one needs right now you do have procedure that computes rate of cooling for electron and hole, but it deals only with energy. This procedure doesn't take care on where
transition.
the excitation is located. Maybe you need a procedure to compute the rate of charge transfer.
Yeah,
And
like for
it may
example,
happen
if you go
quicker.
to your color plots, right, like this one, so you kind of estimated 100 femtosecond where you're creating your charge transfer state, and then your kind of final relaxation, which is also charge transfer state, will take after whatever.
So relaxation takes 1 picosecond and charge transfer takes about 100.
But
femtosecond.
relaxation again to the charge transfer state, right? So your
Yes.
final relaxation also charge transfer in this case. Then you go and then you go to the next, right? Here it happens probably even earlier, right? And then like these types of values also can be put in a table and kind of comparable
Right, yeah.
for easy comparison, I guess, between different excitations and different ligands.
Yeah.
But I think the main conclusion is that this ligands layer on a titanium dioxide, which you call linkage or something like this, definitely differently affect both the charge transfer, the speed of formation, how to say, the quickness of the charge transfer formation, formation of the state with the charge transfer character, as well as overall relaxation times. And it looks like they also differently affect in electrons and holes. And which one is which one you can put kind of, I mean, you can look more carefully and then tell exactly, like, this is just general message, right? And then you can say, yeah, hydroxyls do this and this, and these guys do this and that. And then for deeper analysis of these statements, right, you need to really look more carefully on each of your transitions and each of your orbitals.
Right, yeah.
So based on your calculations, the photoexcited perovskite is able to transfer photogenerated charges to different materials.
Yes.
So the material that you have considered, titanium dioxide, is it acceptor of electron or hole?
Electron.
Okay. Which materials accept holes?
The dyes. So like spirometad or spirometad, however you say it.
Okay. So
But we don't have dyes here.
Not here, no.
But in conclusions, so if you want to build a photovoltaic cell, you need to build interface with both, like on one side titanium dioxide for electron accepting, and on the other side you need the hole accepting material.
But your titanium dioxide is a hole accepting.
In this
Hole
case,
or
it's the
electron?
electron accepting material.
Yellow is a hole. Oh,
No.
backward, okay. sorry.
Yeah.
So it is electron accepting material,
Yes.
for sure.
Yes.
You have numerical evidence and proof of this.
Then
That's
I
right.
don't understand why you need a hole acceptor. Hole is staying on a perovskite.
One
The
needs to-
hole is kind of.
So you just put a lead there, right, at this energy, and then the hole will move to your metallic contact with the right electronic levels, wherever would be right for this energy level.
It may return back and recombine on perovskite if you do not add specific layers that will pull hole out of perovskite. Before you add metal contacts, you need two additional layers.
So I guess ideally you would want this perovskite to stay more or less neutral so that it can keep exciting, I guess.
But it happens really very quickly. 100 femtosecond, sub-picosecond range, you have already your charge transfer. So it probably has really very low chance to recombine back, because recombination will take much longer time, right? You're not expecting that your electron hole recombination will happen in femtosecond range.
If this is
So like if you really have a right contacts at this energy range of your charge transfer state, then you really have no any other channel to compete with such fast.
this could be a discovery of
transfer.
new architecture of solar cell. If this works this way, one can check, and if it is proven numerically that one can skip hole accepting layer, it is much easier to fabricate.
And a lot cheaper too. That was like the most expensive material in it.
It's a pretty old question actually. We already asked that. Where's the bluish atom on the top of the image?
This one?
No, I mean the image, molecular image.
Titanium.
Oh, this one.
Titanium.
Yeah.
And
Wait.
red
There is ambiguity. The cyan color is ambiguous. In the lower portion of the figure, it stands for cesium, and in the top portion of the figure, it stands for carbon.
Oh, for carbon. And where's
It's
titanium?
not
Carbon.
But where's titanium then? What color for titanium?
The red color is
Red is
titanium.
oxygen, right?
No, red's gonna be oxygen.
Yeah,
It
red's
should be
definitely.
oxygen.
Where's
And
the
then where's
titanium?
titanium there?
It's also bluish, bro.
Yeah, and
And where's the
colorblind,
white
so I
color?
can't
So
really
it's
tell
like,
the difference. I have to like
triple
really look at
ambiguity.
it.
Yes.
So is that white color is carbohydrogen, right?
Yes.
Okay. So it's connected through the OH with the perovskite in between the two layer, right? That's a 3 OH.
Where at now? Right here.
Yeah, these are OH, right?
Yeah.
Okay.
That's the linker, right?
There's a
And
linker which-
and the lower part you have the.
So this is a molecules which kind of interact probably with
Interact
both the
probably,
surface of the perovskite and the surface of the quantum dot.
Oh, more questions?
Yeah, it's from the chemistry point of view. How that H hydrogen can interact with the perovskite too, because OH is very stable bond, I guess.
Don't ask me, ask the speaker.
And also
From
OH
the
is
chemistry
negatively
point of
charged,
view,
right?
yeah.
So what you go in with a negative charge here?
You're saying that the bond between the oxygen and the hydrogen is stable, right?
Yeah, so now if I compare the Z-axis, there are a perovskite, there is a hydrogen, and then top of the hydrogen is oxygen, and then top of oxygen is all other things. So it's interacting through the OH bond.
Yes.
So how is it realizable from the chemistry point of view?
Okay, so how is what exactly realizable, I guess? Like the interaction between these and the perovskite?
Yeah, through the hydrogen, through the oxygen bond. Yeah.
There would still be, I guess, well, okay, I don't know how a chemist would think about it.
Make a guess where the models were taken from. It's pity that John is not here.
No,
John,
he's
if you're
here,
here,
yeah, he's online.
He's online, but he
Yeah.
cannot hear or what? Or we
He can hear us, but we cannot.
probably we can put him on, and John will answer this question better than anyone.
So you start with the bulk titanium dioxide surface, right? And you balancing your
Yeah, he's replying. He's typing
Titaniums.
something.
Okay, John, if you are on connection, can you comment on the titanium dioxide cluster?
Sure. In terms of, well, I guess what kind of comment about the cluster are you looking for?
So this cluster is borrowed from your work on polyoxide titanate. Can you just justify their that they're realistic and they're existing in the nature?
Well, yes, they are. They are realistic. You can get coordinates from like single crystal data files that people have taken. So they synthesize these small polyoxide clusters, and then they place them into a type of organic matrix, which kind of holds them separately, and then they take XRD data of those clusters themselves, and you can find that on different databases.
So you are telling they're chemically stable?
Yes, more or less, yes.
Are they neutral or charged?
Yes.
Yes, neutral or yes, charged?
Yes, neutral.
Okay.
But
So-
what is balancing the charge? If it's OH group, it should be negatively charged.
No, it's a whole molecule.
Did you hear the question?
I
What-
did hear the question.
Okay.
Well, I mean, so if it's just an OH group connected to one of the titanium atoms, you're just going to change the coordination number on that titanium atom. It's not so much that there's going to be necessarily an overall charge on the system.
So your oxygen's not balancing your titanium charge, because you should have, like, to have it neutral, TiO2, right? So you have to have, for each titanium there are 2 oxygens, then the system is neutral. But you're saying that even if you have 1:2 ratio for titanium to oxygens, and then put in OH groups, you still...
Oh, no. Here the it is not.
Oxygens are bridging atoms. Like,
John,
so it's methanol.
Just a second, John. Can you tell what is the stoichiometry of the cluster before one places ligands, or if one removes all ligands? What will be the stoichiometry? Will it be 1:2 or some different ratio? Why are they called polyoxytitanate instead of titanium dioxide?
Well, yeah, so the ratios are going to change because there are specific numbers. And I'm blanking on what they are in terms of the ratios between them, but it's not pure titanium dioxide.
So the oxygens from ligands are critically needed to coordinate titanium atoms, because without them titanium will be under-coordinated. Is it right?
Right. Yes.
Oh.
Okay. More questions to John? If no, John, would you excuse putting you off sound, because there is a noise?
Yeah, there's a crying child outside, so that's okay.
Okay. What a silence. So, more questions to London. Any questions from questions from ourselves? No?
Nothing yet.
Daniel? You're happy?
Yeah. Really happy.
Will you be
So we're
able
ready to celebrate 4th of July.
to generate?
already.
Yeah.
Okay, then let's thank London.
Everyone have to ask at least 1 question.
What? We still have a rule?
No rules to everyone has
Well,
to ask 1
let's start
question.
next week.
And if you were making handwritten comments, please submit them to the author so that he can improve and incrementally present the same presentation with improvements.
I just want to announce again, don't forget we don't have meeting this Friday, but we do have meeting next Tuesday. And who's presenting next
Aaron.
Tuesday? Just one?
Yes, but Aaron will be presenting strategic vision of his research, a plan for next paper summarizing different aspects of research. Right? So it will be not just technical, it will be with substantial strategic component. I can aim for that. Okay.
Okay, good. So then, yeah, have a nice holidays.
Yeah, nice 4th of July.
Yeah, happy the 4th.
Now work on your things.